So let's start getting warmed up with dynamics and nonlinear systems. And let's start with the word dynamics. Here's a simple definition. It is the study of systems that evolve in time. Now, such systems may eventually settle down to some equilibrium, or they may keep repeating in cycles, or actually do something much more complicated. Let us now visualize some dynamics. X is the dependent variable, time is the independent variable, there is an equilibrium value, and the trajectories settle to that equilibrium. You can have another scenario where they don't settle to equilibrium, but they actually just keep repeating themselves in cycles. And the third scenario is where you neither have an equilibrium nor a cycle, but you keep doing something which is fairly complicated. Now let's take a historical perspective on dynamics. The story really started in the mid-1600s with Newton. Now what he did was he invented calculus and he worked on differential equations. He then discovered his laws of motion and universal gravitation, and he combined them to explain Kepler's laws of planetary motion. Now essentially what he did was solve the two-body problem, which is calculating the motion of the Earth around the Sun given the inverse square law of gravitational attraction between them. Now what proved to be rather difficult was the three-body problem. That is the problem of the Sun, the Earth and the Moon. This turned out to be a very difficult problem to solve. In the sense of trying to obtain explicit formulas for the motions of the Sun, the Earth and the Moon. Progress then happened in the late 1800s with the work of Poincaré. Now what he really did was introduce a brand new point of view. What he said was the following: let's focus on qualitative rather than quantitative questions. Here's an example of a quantitative question. Can we find the exact position of the planets at all times? Here's a qualitative question. Will our solar system be stable forever? In other words, might some of the planets suddenly decide to leave the solar system and go off to another galaxy? Now what Poincaré did was develop a geometric approach to answer such qualitative questions. Now let's move on to the first half of the 20th century. Dynamics was largely concerned with nonlinear oscillators with applications in physics and in engineering. Now this led to the development of the radio, radar, phase-locked loops and lasers. In the second half of the 20th century, computers started to allow us to visualize complex dynamics. Edward Lorenz, in a famous 1963 paper, observed chaotic motion in a simple model for atmospheric dynamics. Later in the 1970s, working in mathematical biology, Winfrey worked on nonlinear oscillators like heart rhythms. In physics, Feigenbaum went on to establish connections between chaos and phase transitions. And in the 1980s, there was a very famous book by Kuramoto called Chemical Oscillations, Waves and Turbulence. Now, moving on to the beginning of the 21st century, the key words that one often hears are complex systems and networked systems. Now, usually such systems are large-scale and highly nonlinear, and there are applications all over science and engineering. Now we start talking about dynamical systems. There are two main types of dynamical systems. One is differential equations, where the evolution of the system happens in continuous time. The other variant is difference equations, where time is discrete. We focus on differential equations as these are widely used in science and in engineering. A very general framework for ordinary differential equations, abbreviated as ODEs, is x1 dot is equal to f1 x1 to xn all the way up to xn dot is equal to fn x1 to xn. The overdots represent differentiation with respect to time t. So the xi dots is equal to dxi dt. The variables x1 to xn could be concentrations of chemicals within a reactor, or they could be populations of different species within an ecosystem, and so on. The functions f1 to fn are determined by the specific problem at hand. As an example, let us consider the damped harmonic oscillator. Here's the differential equation. That's m d squared x dt squared plus b dx dt plus kx is equal to 0, where m, b and k are greater than 0. Now, this is an example of an ordinary differential equation. Now, what we do is we introduce new variables. x1 is equal to x and x2 is equal to x dot. Then x1 dot is equal to x2 and x2 dot is equal to x double dot, which is equal to minus b on m x dot minus k on m x, which is minus b on m x2 minus k on m x1. The equivalent system then turns out to be x1 dot is equal to x2 and x2 dot is equal to minus b on m x2 minus k on m x1. Now recall the general form of the ordinary differential equations. That is, x1 dot is equal to f1 as a function of x1 and x2, and x2 dot is f2 as a function of x1 and x2. So if f1 is x2 and f2 is minus b on m x2 minus k on m x1, then we've essentially just turned the damped harmonic oscillator into the general form of the ODEs that we had earlier. Now here are some notes. The above system is linear, as all of the xi's on the right hand side are to the first power only. For a non-linear system, typically the terms are products, powers and functions of the xi's. For example, x1, x2, x1 squared, sine of x1, etc. are all examples of nonlinear terms. Now let's consider the example of a swinging pendulum. The differential equation is x double dot plus g on L sin x is equal to 0, where x is the angle of the pendulum from vertical, g is the acceleration due to gravity, and L is the length of the pendulum. The equivalent system is x1 dot is equal to x2 and x2 dot is equal to minus g on L sine of x1. Now we get to this equivalent system using exactly the same trick as the previous example. This system is nonlinear because of the sine x1 term. Now this makes the equation very difficult to solve analytically. Now we can use the small angle approximation, that is sin x is approximately equal to x for x much less than 1, which will turn the equation into a linear one. But we will also try to extract information about the original nonlinear system using geometric methods. The rough idea is as follows. Now suppose that for a particular initial condition, we just happen to know the solution to the pendulum system. The solution could be a pair of functions x1, x2, representing the position and the velocity of the pendulum. Now if we construct an abstract space x1, x2, then the solution x1t, x2t will correspond to a point moving along a curve in this space. Now let's just go ahead and plot this. So we have an initial condition x10, x20. We go ahead and plot a curve. Now this curve is called a trajectory. The space is called the phase space. Now the phase space is actually filled with trajectories, as each point can actually serve as an initial condition. Now we outline Poincaré's geometric perspective. Now, given the system, we want to draw the trajectories and thereby extract information about the solutions. Now, in numerous cases, such geometric reasoning actually allows us to draw trajectories without actually solving the system. Here are some notes. The phase space for the general system is the space with coordinates x1 to xn. So n represents the dimension of the phase space. So the space is n-dimensional. Now phase portrait is just the collection of all the qualitatively different trajectories in the system. Now let's have a brief discussion on linear versus nonlinear systems. Now when you look at linear systems, they can be broken into parts. Then each part can be solved separately and then recombined to get to the final answer. Now they are equal to the sum of their parts and utilize methods like Laplace transforms and Fourier analysis. So a natural question to ask is, given that we have such a rich theory for linear systems and very well established methods, and they behave nicely, then why not just model using linear systems? The answer is as follows. When parts of a system interfere, cooperate, and compete, we very naturally get nonlinear interactions. Additionally, most systems in science and engineering do not really act like linear systems. Now here is one way to look at the world of dynamics. On one axis we write down the dimension of the phase space, and on the other axis we classify systems as linear or nonlinear. Then our current focus will be on this regime where we'll be dealing with one and two dimensional nonlinear systems.